Let's start with a quick review of insulating sheets and conductive plates. And of course, I'm talking about infinitely large sheets and plates. For an insulating sheet, an infinitely large sheet of charge, the charge can be very, very thin. It can really be one layer. And if it has a charge density sigma insulator, sigma I, I'm calling it here, we can use Gauss's law and come up with the electric field near this sheet, and we get sigma over 2 epsilon naught. If we do the same thing for a conductive sheet or plate, we put some charge on it and it immediately splits. Half is on one face of the plate, half is on the other face. When we say sigma equals something, sigma equals 4 coulombs per square meter or whatever it is, we mean on only one face, and the opposite face has the exact same charge if there are no other charges present. The charge will split equally if there are no other charges present. And we can use Gauss's law, and we get the electric field is sigma over epsilon naught. It looks like we're off by a factor of 2 from an insulator to a conductor. But really, if you think about it, if you're outside looking in at this sheet of charge, you don't care whether it's an insulator or a conductor. If there's a total of 10 coulombs per square meter, you should measure the same electric field. Well, if the sigma conductor is equal to half the sigma insulator, then the total charge there per square meter is the same as we talked about in the last lecture. Half of it is on one side of the conductor and half of it is on the other face. But the total would be the same as on the insulator. And then you get the exact same electric field. It really has to do with the way sigma is defined. Now, another thing that we can do with conductive plates, if we know how the charge splits, we can treat them as two insulating plates. It's the same thing. So if I have a conductive plate here, and I know that I have a certain sigma on each side, sigma naught, on each side of that plate, that's equivalent to 2 insulating plates where the charge density on each of these sheets is sigma naught. I can split that conductive sheet and make 2 insulating sheets with the same charge densities and calculate all my electric fields, and I get the exact same answer. But I have to know what sigma is. And the tricky thing with conductors is that charges can move. So let's take a look at this example. I have a conductive plate, and when it sits all alone in space, it has a surface charge density of sigma c. That means on the left side, there's a surface charge density of sigma c, and on the right side, there's a surface charge density of sigma c. If there are no other charges present, I know the charge will split equally between the 2 faces of my conductive plate. But if I bring another charge next to it, if I bring a insulating sheet of charge over here, the charges on my conductor are going to be attracted or repelled by that insulating sheet. If these charges are positive and this is negative, the negatives will attract more positives. So some of the positives from the other side are going to move over and show up over here because they're attracted to this negative sheet I just put next to it. If it was the other way around, if they're like charges, if I bring a positively charged insulating sheet next to my positively charged plate, conductive plate. Those charges repel each other, and some of these positives are going to move around to the other side and end up on the back side. And then those two charge densities will not be equal anymore. They will be different. They can change. So the question is, what is the new charge density on each side of this conductor if I bring an insulating plate next to it? I'm going to continue the problem I just started. I have a conductive plate, an infinitely large, flat, conductive plate, and it has a charge density sigma c when there are no other charges present. I have an infinite sheet, insulating sheet, that's charged with a charge density sigma I, sigma insulator. And it doesn't matter whether there are charges present or not, that can't change, right? It's an insulator. If we put a certain amount of charge on that surface, it's going to stay there. Those charges can't move. So sigma insulator, we don't have to worry about. That's going to be the same whether we have a charged plate next to it or not. But those sigma c's that are on the conductive plate, when I bring another charge next to it, those are going to change. Charges are going to move, and those are going to change. So let's take a look at our situation now. We've got our two charged objects in close proximity to each other. The insulator has a charge density sigma insulator, sigma I. And the conductive plate, we don't know what those charge densities are going to be. I'm going to call this one sigma left and this sigma right, just for the left side and the right side of our conductor, for lack of a better term. Now, what do I know about sigma left and sigma right? I know something about that charge already. If I have a conductor that has sigma c on each side of it, and I bring another charge next to it, and some of those charges move over to the right side or to the left side, back and forth, what do I know about the total charge? It has to be the same, right? It didn't change. Nothing touches this sheet where the charges can leave. Nothing adds more charge. It's just redistributing itself from the right side to the left side and vice versa. So right off the bat, I have an equation. I know that sigma left plus sigma right is equal to 2 sigma conductor, right? The total charge has to be the same. Total charge is the same. Now we know some other things. What I'm going to do is treat each side of that conductor. Once the charges move and redistribute, they're not going to move anymore. They're going to stay in a steady state. It's going to find an equilibrium state. I can treat that conductor like an insulating sheet with charge density sigma left and an insulating sheet with charge density sigma right. And I know I've got my insulator over here, sigma I. And I can look at the electric field everywhere based on these 3 infinite insulating sheets of charge. I can only do that once these charges stop moving, once they've redistributed themselves and I know what they are. So I'm just going to call it sigma left and sigma right. Sigma left, I'm going to use blue for sigma left. And I'm going to assume that these are all positive, because if I do that, you'll see in the end, if I got the sign wrong, it self-corrects. If I assume they're negative and I get the sign wrong, it doesn't self-correct at the end. So I'm going to assume all of these are positive. If there's positive charge on this sheet we're calling sigma left, what does the electric field look like? Well, it comes out from that sheet in all directions. So I'm going to have an electric field here and here, and it's going to just continue everywhere as we move away from this sheet. The electric field will be constant. And I'm going to call that E left. Now the right one, let's use gray for the right side. If that was a positively charged sheet, it would send electric field out from it, and that electric field would keep going. So this would be E right. And our insulating sheet, I'll use green for my insulator, will send electric field out in both directions. Now I can figure out the electric field in any of these regions. The electric field in this region, to the left of all of our charges, is equal to the sum of the three sheets of charge that are creating the electric field there. The electric field between the two is a combination, and the electric field to the right of all of them is also a sum. Those don't really help me yet, but what does help me is the electric field inside of my conductor. I'm treating my conductor like two insulating sheets of charge, but it's really a conductor. And I know that in a conductor, once it reaches electrostatic equilibrium, the electric field has to be zero. So in this region here, the electric field has to add to zero. So let's do that. That gives us a nice equation. I've got the E left plus E right. This is a vector addition. Plus E insulator has to be zero. This is a vector addition problem. So I'm going to call this my positive direction. The right is going to be my positive direction. So E left points in the positive direction. What is the electric field from an insulating sheet of charge? It's sigma over 2 epsilon naught. And it's in the positive x direction. What is the electric field from the right charge? It's going to be sigma right over 2 epsilon naught. And it points in the negative x direction. And then I've got a sigma insulator over 2 epsilon naught in the negative x direction. And those have to add to be zero. That means that I don't really need my unit vectors anymore. That means that sigma left over 2 epsilon naught minus sigma right over 2 epsilon naught minus sigma insulator over 2 epsilon naught equals 0. And of course I can multiply through by 2, and I can multiply through by epsilon naught, and I get sigma left minus sigma right minus sigma insulator is 0. Now let's think about how I did this for a second. I assumed that all of my charges were positive when I set this equation up. Of course, they're not all going to be positive. But let's think about what happens if I'm wrong. I have this equation here, and if I'm wrong, if sigma left is really negative, and I put a negative number in here for sigma left, it now will change this to a negative number. It'll point in the negative x direction. If I put a negative number in for sigma right, it flips the sign and it now points to the right, the positive direction. It self-corrects at the end. If we're wrong with the sign here in this equation, it self-corrects. That's why I always assume positive to start with. So I have one equation here, but I have two unknowns, sigma left and sigma right. I don't know what they are. Sigma insulator was given, right? That I know. I have two unknowns. Luckily, I have another equation. Sigma left plus sigma right has to equal 2 sigma conductor, and sigma conductor was given in the problem. Those were the two givens, sigma conductor and sigma insulator. Now we're trying to find how does that sigma conductor split to sigma left and sigma right after we move an insulating sheet next to it. So I have two equations and two unknowns, and I can solve those. If you'd like, we can just throw in some numbers and solve it real quickly. Let's let sigma conductor be, what should it be? Positive 4 coulombs per meter squared. And let sigma insulator be, what would you like? How about negative 7 coulombs per meter squared? So that means that sigma left plus sigma right is going to be 2 times 4, or 8, and sigma left minus sigma right minus a negative 7 has to be 0. I can substitute in sigma left is 8 minus sigma right minus sigma right plus 7 is 0. And what do I get? Minus 15 is minus 2 sigma right, or sigma right is positive 7.5 coulombs per square meter. And what would sigma left be? Sigma right plus sigma left have to add up to 8. So it would be also positive 0.5 coulombs per square meter. Let's summarize what we've learned so far. We've done 2 chapters in our book. One technique to find the electric field from a continuous charge distribution was to treat every little tiny element of the charge, dq, like a point charge, and find its electric field, k dq over r squared, and integrate, add them all up to get the net contribution at our point of interest. Our second technique was to use Gauss's law. The integral of E dot dA over a closed surface is equal to the charge inside our surface over epsilon naught. These are both techniques that involve integration. These integrals can be ugly. We want to pick the technique that gives us the easiest integral to solve. Gauss's law is really only easy to solve in a few cases. Spherical symmetry, point charges, spheres of charge, a spherical shell of charge, things like that. Cylindrical symmetry is also a useful time to use Gauss's law. And in order to have cylindrical symmetry, our object has to be infinitely long. A line of charge, a cylinder of charge, something like that. If it's not infinitely long, we don't have cylindrical symmetry because we get edge effects. The electric field lines are not going to come out parallel to each other. They're going to start to diverge at the ends. It has to be infinitely long for cylindrical symmetry. And the last situation where Gauss's law is really useful, infinite sheets of charge, either insulating sheets or conductive plates. Infinite sheets of charge.